Here is an introduction to the Drake equation to accompany Chapter 30 of the textbook Astronomy from Open Stax. A question that you may naturally have, or at least would come up if you're thinking about life in the universe, is how many intelligent, communicating extraterrestrial civilizations are out there? And if we want to answer that, there's a lot of unknowns. But there's a thing called the Drake equation that it's a tool to help us approach this question in a semi-quantitative way. As you'll see, it by no means will give any kind of definitive answer. There are just too many unknowns. But it's a way to help you think about this problem and to give a really rough estimate just based on some best guesses. Now, this is probably an overly simplified way to look at it. There's a lot of complicated things involving life developing in the universe, as we've talked about in the past. But if we want to try to make the problem, as I would say, as simple or as close to as simple as possible, then the number of civilizations that we could communicate with is going to be determined by the rate of star formation. So, you need stars to have civilizations. The fraction of those stars that host planets. Of course, we don't care about just planets, but habitable planets. So how many of the planets in those systems are habitable? What's the fraction of those that develop life? Of those, what's the fraction that develop intelligent life? Of the ones with intelligent life, how many develop the ability to communicate over long distances and choose to do that? And then finally, what is the lifetime of this communicating civilization? So when we put it all together, we get this as the classic Drake equation. And we basically have a few parameters that we can determine with a decent degree of accuracy. So star formation we can constrain to within a factor of a few. Same with the fraction of stars with planets. That's relatively certain. Number that are habitable, we can at least do that within a couple orders of magnitude. So it's at least quantifiable. And then, of course, all these others are very speculative because there's only one place in the universe we know that there's life. That's Earth. That's where we have intelligent life. We sort of communicate, as I'll mention in a bit, and we know we've at least existed for a little bit. So these ones, as we'll talk about, there's a little bit more philosophy that goes on in estimating these parameters. And that's, again, why keep in mind the whole time, the Drake equation is just a tool to help us think about whether or not communicating with extraterrestrial civilizations would ever be possible or plausible or not. Let's just step through the parameters in the Drake equation. So beginning with the rate of star formation, the way this is determined, or one way this can be determined, is you figure out the mass of stars in the Milky Way. So you can use gravitational lensing, you can use the luminosity, you can use various different ways. So you determine what's the mass of stars that we have, what is the initial mass function of stars. So we talked about this in Introduction to Star Formation. And then what are stellar lifetimes? We know those pretty well. You put all those things together, and given the mass of the stellar mass is created per year is about 1, and your average stellar mass is less than 1 solar mass, something like a few stars per year. You could call this 1, you can call it 4, whatever. So roughly 4 stars per year. And that one we know decently well, within a factor of a few. Now, as far as the fraction of stars with planets, thanks to exoplanet research, we believe this is probably something like 1. It's a little bit difficult because if you look at the sensitivity of detecting a planet, we're limited right now with detection techniques to higher mass planets that are sort of closer in to their host star. And so, we can't see a lot of planets that are lower mass and not that close to the host star, especially just lower mass in general. And so there's a bias here that we're missing a lot of planets. So for instance, if we were to try to detect planets in a solar system like Earth, we wouldn't be able to see Uranus or Neptune or Earth, at some nominal distance. But nonetheless, if we know what these sensitivity limits are, based on planets that we can observe, we can construct a planetary mass function. So what's the fraction of planets created with a given mass. And taking that all into account, it seems like that pretty much, on average, every star system has planets. Some we know have zero, but many star systems have many planets. So this fraction is probably something like 1, and that's not terribly uncertain. Again, maybe factor of a few or something like that. Now we need to consider the number of planets that are habitable. And what's fun is when the Drake equation was first proposed, this was a much more uncertain parameter, and exoplanet research has made major advances, and so this is a sort of more quantifiable thing. Now, habitability, as we talked about in the introduction to habitability, it depends a lot on what you consider to be habitable, right? So there's lots of ways an environment can be habitable. If you take a relatively closed-minded view and you say, okay, the planet mass has to be similar to Earth so that it's rocky, and the amount of radiation on the planet has to be something like on Earth, then you can, for instance, construct a box and you can count how many planets you see are within this box. And that gives you an idea of what the total number of habitable planets is compared to all the other planets that you've detected. So if we take this sort of really restrictive criteria and we say rocky surface ability to sustain water, you can, for instance, go to this website here, this group at Arecibo. They say that there's about 60 or so exoplanets that are habitable in terms of being Earth-like conditions. And the total number of exoplanets right now that we know of is something like 4,600. Okay, and you can probably double this number of 60 just based on the fact that moons in those stellar systems may also be habitable. And I come up with the factor of 2 just based on, if you look back at introduction to solar system life, there's about as many moons that could be habitable in our solar system as there are planets. So something like 0.02 isn't an unreasonable number. There are many arguments you can find if you look at the scientific literature or just Google on the internet that arguments based on detection bias and being more open-minded about habitability, this number could actually be 1. So in principle, there's a case to be made that every stellar system that has a planet, which is most of them, has a planet or a moon that is potentially habitable. Now we move into the territory of getting into philosophy a bit. Okay, so what of those potentially habitable planets, what's the fraction that actually develops life? So we can think of arguments in favor of there being a high fraction is that life on Earth, developed within the first couple 100 million years, or at least within the first billion years. We talked about that in Introduction to Solar System Life. So that would suggest that since life developed pretty much right after conditions were favorable for it, that it should be pretty common if you have the right ingredients. And there's also this idea of the mediocrity principle. You're not special. So if I were to take a random draw from any given sample, I'm likely to get a pretty average thing, right? Whatever I draw from that sample is likely to be average relative to everything else. And so if you think of us existing as a random draw, then in principle, life should be pretty common on a habitable planet. However, there's some obvious issues with that. One is that it's not a random draw. We happen to be where we are, but who knows how random that is. Also, life on Earth, if you look at the genetic code, we all have the same kind of genetic building blocks, very similar protein sequences, and so it seems likely that we on the Earth have a so-called universal common ancestor. And that would suggest that basically life kind of developed once on the Earth and then all developed from there. And the Earth's a big place, so that would make life on a habitable object pretty rare. A counterpoint to that is just because we find one universal common ancestor now, doesn't mean that there weren't lots of competing ones and only the fittest survived. So that's a counter argument to that. Another thing in favor of life being rare is we have some plausibly habitable bodies in the solar system, and yet Earth is the only one that we have signs of life on so far. Obviously, if we detect some sort of microbial life elsewhere in the solar system, that's going to make this number, this fraction of habitable planets with life, go way up. At least that's the argument. A counterpoint to that is perhaps life began in one place, and then because of meteorites, there was contamination to other objects, and so that's why you have other life in the solar system. So if you really want this to be a slam dunk, you need to find life elsewhere in the solar system that has sort of a different set of building blocks. A real slam dunk would be methane-based life on Titan, for instance. Another thing in favor of life being rare is when you do these Miller-Urey experiments that we talked about in Introduction to Habitability. We so far haven't come up with anything that creates that creates molecules resembling a cell or anything living. So it's obviously not totally trivial. If we want to be humble here and not be egotists, we can call this 1. Why not? Life developed on Earth. So, just because we don't want the conversation to end here, let's call it 1. Okay, and then the next big step is you not only need life, you need intelligent life. And this is going to depend a bit on what you call intelligent. So some would argue that if you have life, there's a really high probability you'll get intelligent life. So one reason is that when you look at the evolutionary record on Earth, you'll see it gets more and more complex with time. So that would suggest that nature just tends to ultimately develop intelligent life. Another issue is that this so-called mediocrity principle, where here, as we said, you are not special. And then additionally, if you treat each species on Earth as a separate experiment, which is a little bit ridiculous, but let's just go with it. There are lots of intelligent creatures on Earth that can communicate with each other, socialize, use tools and whatnot. So maybe it's not all that rare. Perhaps if you gave some of these other species long enough, they would or will eventually become as intelligent as we are. Who knows? In favor of a low fraction is that, okay, if you're really strict with your definition of intelligence, it's just humans on Earth. We're the only ones that have a reasonable shot at any kind of extraterrestrial communication. So that would suggest a low fraction. Another thing is that, let's say that there is other life in the universe, like let's say that we do ultimately find microbial life on Mars or signs of past microbial life, that's totally plausible, but it's pretty clear there wasn't intelligent life on Mars, right? We have no signs of any kind of civilization, so it seems doubtful. So that would suggest that just because you have life, this is, again, I'm just saying that there could be microbial life on Mars. We have no evidence. If there is, then intelligent life still is kind of rare. Another issue is that it takes a long time to evolve, right? On Earth, it took, billions of years to finally get to intelligent life. So you need to not only have these nice conditions for habitability and nice conditions for life to exist, but those conditions need to be sustained for quite a long time. So, this number could be as small as you like. You could end the conversation here and say it was just a really rare development that life developed on Earth, and you could end it here, or we can just be humble and say, let's just call it 1, right? That's an optimistic view. And one that I kind of like, it's still pretty optimistic, but it's maybe a little bit more realistic, is let's say that all of the potentially habitable environments in the solar system, let's say that they all have microbial life, and Earth has intelligent life. And then also, Earth is only going to have intelligent life for about half of the lifetime of the sun. So then, taking all those things into account, I get a number of 0.05 for this fraction that develop intelligent life. So that I think is not an unreasonable. It's a mildly pessimistic number, but at least with some kind of mathematical basis to it. So now we need to think about the fraction of intelligent life that will develop the ability to communicate. This, of course, makes assumptions about that we can even detect the communication. When we think about communication, it could mean a lot of different things. There's some fun articles you can read out there. So for instance, the traditional way of looking for intelligent life is with radio communication, and a little bit with lasers maybe. You could use those different forms of electromagnetic radiation to communicate. A really sort of sci-fi, but quasi-plausible method would be to use transits. So a very advanced civilization could create, large artificial satellites to create transits around their star that would then be used to encode messages to distant civilizations. So obviously this would take a whole lot of energy, and you'd have to be just unimaginably advanced to do this. Or I guess not unimaginable, but way, way more advanced than we are. But this signal would persist for a very long time, right? Your artificial satellite would exist for thousands or even tens of millions of years, as opposed to if you construct a really strong radio transmitter, what's its lifetime going to be? A century, a few centuries, not that long. And so the point here is that communication can be defined lots of different ways. So our communication is relatively puny, right? So we have radio telescopes, and we can generate radio signatures. The strongest radio signature that we've ever generated was from Arecibo. And if we consider this strongest radio signal that's ever been generated on Earth, and we take a look at near future, current and near future telescopes, we could only detect that Arecibo signal out to a few thousand light years. That's the strongest radio signal we've ever generated on Earth. If you consider, more average radio signals, one we're generating all the time, every day, like military radar, then we could detect those types of radio signals with current generation and near future radio telescopes out to a few hundred light years already. So if there were intelligent life out to a few hundred light years and it was comparable to ours, we would have already detected it by now, in all likelihood. So still, what's this fraction of intelligent life that creates communication? Let's just appeal to mediocrity again, and we can just assume 1. If you're intelligent, you're eventually going to develop the ability to communicate with extraterrestrial systems. So the last term here is L. This is the lifetime that your communicating civilization is actually communicating, right? So it's going to depend on how long that civilization survives and how long it chooses to communicate. Maybe smart civilizations decide not to communicate after a while, or not at all because they don't want to be found out. I mean, think about it. Right now on Earth, if a signal that we sent were to reach an extraterrestrial civilization and they were able to act on it, they would be way more advanced than we were. So that's a little bit of a scary thing if you think about it. So maybe you'd choose to hide. If we want to take the most optimistic view, in my opinion, of how long a communicating civilization could communicate for, it would basically be the viable lifetime, the viable habitability of that planet. So on Earth, intelligent life is around basically like now, and we know that within about 1 billion years, because of the steady increase of the temperature of the sun, that the temperature on our planet is going to rise. And at a certain point, because of increasing water vapor in the atmosphere and a corresponding greenhouse effect, it's going to get as hot as Death Valley in about 1 billion years. And within 2 billion years, there's going to be almost all the water's gone. There'll be no water-based life at all. So a pretty optimistic view is that we're going to be able to communicate for the next 1 billion years. That's as optimistic as you can get, I think. A more pessimistic, but probably more realistic view is that you got to look at major extinctions that have happened on Earth. And around every 30 million years or so, there are mass die-off events for different reasons: volcanic activity, asteroids, disease, what have you. So we have these mass extinction events 30 million years. So that's still pretty optimistic, saying that we can communicate for that long. I would say very pessimistic view, but probably the most realistic, is that civilizations blow themselves up, right? If you think about what's the odds of us all killing ourselves within the next century, they're non-zero. So, or at least a few hundred years. And if we take a look at major civilizations on Earth, they usually only last a few centuries. Depending on how you define Rome, you're talking about a couple hundred to maybe 500 or so years for Roman civilization. So that's not an unreasonable number to choose here in terms of L. So now let's put this all together and let's use our estimates to calculate N, the number of communicating civilizations in the Milky Way. So taking our high end, we plug in all those numbers that I went through. We'd say that there are about 4 billion communicating civilizations in the Milky Way, which is a huge, huge number. Just to be a little bit of a Debbie Downer here, the issue is that with radio telescopes, we can probably rule this out already. So as I mentioned, with our current radio telescopes, we can detect military radar type signals out to a few hundred light years. And a few hundred light years from our sun comprises, around 1 million stars, ballpark. And there are about 100 billion stars in our galaxy. And so, around 10 to the minus 5 of all stars are in the Milky Way. So if you multiply these two numbers together and you do some rounding, we should be able to detect thousands of communicating civilizations, and at least so far we don't think that we have. So that means, probably one or likely many of these numbers here are overestimates. So if we want to be a little bit more conservative, let's take the non-zero but lower numbers that I came up with on the previous slides here, and then you'd say that there's about 100,000 or so civilizations in the Milky Way, which is plausible. That means that we wouldn't have necessarily detected one yet, but we could detect one very soon. And if we want to be even more conservative, we want to take these not completely pessimistic, but I'd say quasi-realistic estimates, and also assume that we're going to blow ourselves up here, in a century or so, then that would indicate that basically we're the only civilization, intelligent communicating civilization in the Milky Way. But on the bright side, that would mean that nearby galaxies might have intelligent communicating civilizations. Of course, they're not nearby enough for communication to really mean anything, so that you can't get by the light travel time. But nonetheless, there could be intelligent communicating life near-ish by, even if you're relatively pessimistic. If you take a look at sort of the wisdom of the crowd, what is everyone not everyone, what have a lot of people who've spent a lot of time in the scientific literature estimating these parameters, what do they think? That's shown with this distribution here. So you're looking at the frequency of the estimate of this number n, and this is a log scale, and you'll see that the wisdom of the crowd peaks at around several tens of communicating civilizations in the Milky Way. So a decently high, quite a few civilizations that we could communicate with. The really interesting thing is if you say that this number is true, several tens, and you assume that they're kind of spaced somewhat arbitrarily in the Milky Way, the nearest one would be a few thousand light years away. And that puts us in the communicating range in the near future. So with telescope technology that is planned right now and radio signals that we could plausibly generate now or maybe in the next several decades, we would be able to detect and communicate with those civilizations. Now, of course, the signals we receive would be thousands of years old because of light travel time. The ones they receive would be thousands of years old, and they wouldn't receive them for another 1,000 years. But nonetheless, it's actually kind of plausible that there could be communicating civilizations that we'll detect soonish. It's at least not it's not completely unreasonable to say that. So there is this pessimistic view or viewpoint that people like to bring up. It's called the Fermi paradox. So the question is, if life is so common, why don't we see it, right? One reason is that it could be that one or more of those Drake equation parameters are really small, and people call this the great filter. So basically, maybe forming life is uncommon, maybe forming intelligent life is rare, maybe civilizations aren't around for very long because they blow themselves up. That could totally be the case. If you take this still relatively optimistic view, based on the wisdom of the crowd of the number of communicating civilizations in the Milky Way. And if you integrate that, you still get that there's about a 25% chance that even, based on this wisdom of the crowd, that we're alone in the Milky Way. And there's like a 10% chance or so that we're alone in the observable universe. Now, I wouldn't take these numbers too seriously because remember, this blue distribution is based on a whole bunch of people's guesses. But still, the great filter, again, plausible based on reasonable assumptions. Before you get discouraged, though, keep in mind what I mentioned a moment ago, that our ability to detect signals isn't that great, right? We can only detect civilizations like ours within a few hundred light years, and soon we'll be able to reach a few thousand light years. But with that given few hundred light year estimate, there could easily be tens of thousands of communicating civilizations in the Milky Way, which I think of as like a Star Trek type universe. That is actually not unreasonable for that to be the case. Now, as our ability to transmit and receive signals improves, we're gonna beat that back a little bit. We'll either start to detect civilizations or we won't. And so that means we can use this Fermi paradox in reverse. So as we continue to not see intelligent life, we can place limits on some of those parameters in the Drake equation, which is kind of interesting. This is it for this introduction to the Drake equation for Astronomy 1000.